So in this video, we will be going over a math problem involving the method of proof by induction, and also incorporate some trigonometric identities. So if you're not familiar with trigonometric identities, then I strongly recommend you to go back to my algebra playlist to watch some of the trigonometry series, because it will you will need to know some of the formulae in order to effectively solve this problem using the proof by induction. So the problem says, it's from the IB Maths HO November 2016 paper 1, and it says to use the principle of mathematical induction to prove that this sine x plus sine 3x all the way up to sine 2n minus 1x is equal to 1 minus cosine of 2nx over 2 sine x for all positive integers n, where x is not a multiple of pi. So also, like, if you haven't watched my introductory video on the proof by induction, then I really recommend you to watch that video too, because I won't be really explaining it from the basics again here, but just straight away going into using this to solve the problem. So like I said in the previous video, and then in the introductory video, I actually kept saying for the first step that you're proving the initial case true. But normally in math class and math teachers call it the base case actually. So apologies for that. For the base case, we prove it true for the smallest value in the given domain, but you can call it the initial case too, it doesn't matter. So for an n equals 1, because 1 is the smallest positive integer, we want to see if this holds true for n equals 1. So the left hand side, actually let's do the right hand side first because it's spicier. So if n equals 1, then the right hand side is equal to 1 minus cosine 2x over 2 sine x. And then cosine 2x is just equal to 1 minus 2 sine squared x. And then this is equal to, so these will cancel out. And we notice that then it's 2 sine squared x over 2 sine x, which is just sine x. So simple algebra to see that this is equal to sine x, and then the left-hand side for n equals 1 would just be sine x. So we proved it true for n equals 1. Now we do the inductive step. And I'll actually put this in a different color because I actually don't have that much space, so I need to color code this a bit. So we're gonna assume true for, my handwriting is really messy today, for n equals k, i.e. we are assuming that 1 minus cosine 2kx over 2 sine x is equal to sine x plus 3x, sine x plus sine 3x all the way up to sine 2k minus 1 x. Do I have space for this? I'll write this at the bottom because our next proof will be quite spicy. It'll take a lot of space. Sine 2k minus 1x. Yeah, that took a long time to write. So we're going to assume that this is equal to, so we're assuming this is true for n equals k. So we want to show that if this is true, then it will be true for n equals k plus 1. So we want to show that sine x plus sine 3x all the way up to sine 2k minus 1x plus sine 2k plus 1x equals 1 minus sine 2k plus 2x over 2 sine x. So we're going to write the sum. We're going to start with the left-hand side first. This. So we want to prove that this is equal to 1 minus cosine of 2k plus 2x over 2 sine x. And like I said before in the introductory video, if you have a sum, then it's really easy to use a proof by induction, because you can easily incorporate this into proving it for n equals k plus 1, because you can just split the sum. So I'm going to split the sum here so that I can, sorry, I wrote that wrong. It's sine 3x. Sorry for any confusion. Sine 3x plus all the way up to. So if you split it so that we can include it, so we're going to include up to 2k minus 1. This actually is really important to know the motive behind how you solve induction problems, because really the hard bit is where you find how to start the inductive step. So yeah, we can just directly substitute this in to get this will be equal to cosine 1 minus cosine 2kx over 2 sine x plus sine 2k plus 1x. And then this is equal to, we're just going to bring this up, 1 minus 2kx plus 2 sine 2k plus 1 x. I'll write that again. Sine x. Yeah. Yeah, so that is what we got. And it looks nowhere like this. And it looks nothing like this. But we can actually, for those who are familiar with trigonometric identities, you'll notice that you can do something with this product of sines. And actually, if you get a product of sines and you want things to cancel out by addition, then of course you should use the product to sum and sum to product formulae. I'm not going to go over the proof for the identity for the formula, but I'll just write it up here so that we can recap. So we know from the trigonometry videos that sine A times sine B for any real values A and B is -½ times cosine of A plus B minus cosine of A minus B. Yeah, I'm writing it on top here because it's really important. So actually you can really easily prove this. So for those who have seen this for the first time, maybe you can go ahead and try prove it. But yeah, so now that we know this, we can just convert this into a sum of cosines, and that's a good idea because we want to cancel this out from here. So by addition, so by converting this to a sum of cosines, we can easily, maybe we can find a way to cancel this out. So let's see if that's right. So we'll just write the other things first. That line was not straight. Oh my god. Good enough. So if we multiply 2 to this, then the half just disappears, and there's also minus, so it becomes a minus. So A is 2k plus 1 in this case. Yeah, I'll just yeah. A is 2k plus 1 and B is x and oh, that's not x. Oh wait. Yeah. So A is 2k plus 1x, and B is x. So A plus B, so cosine of A plus B would be 2k plus 1x plus x, which is 2k plus 2x. I just confused myself for a second, sorry. And then it will be minus cosine of A minus B, which is 2k plus 1x minus x, which is 2kx. I like where this is going. So actually, if you look closely, you can just cancel this out. You don't even need to look closely. It just cancels out. And then you get 1 minus cosine of 2k plus 2x. It's all being crammed in here. Over 2 sine x. And it turns out that it is actually what we wanted to get at. We wanted to prove that this sum, if this is true for k plus 1, then the right hand side should be equal to this expression. So we proved it true for n equals k plus 1. That's good, because we showed that. So we're going to write the last line for this proof, because we have actually completed this proof. So therefore, we have proved that if true for n equals k, then it's true. Okay, my pen isn't working very well today. For n equals k plus 1. And we know that it is true from the base case, or like the initial case, and it's true for n equals 1. Therefore, it is true for all n in the positive integers. Yeah, so or you can just add like a phrase like by the principle of mathematical induction, if you want to be kind of specific or like precise about your language. But yeah, this line will just do, because you've shown that, yeah, by these two steps you have proved it's true for all n in the positive integers. So yeah, this is actually a really nice problem, because it uses content learned, some good trigonometric identities used from previous videos that I've made. And yeah, so basically, so this is a new way, so this is a pretty interesting problem, because it uses you have to be kind of skilled or like creative at noticing how, and in this step to recognize what to do, because you want to have some way to find a cosine 2k plus 2x, and you want to cancel this out by addition actually, because this is subtracted from something. And you can straight away, if you're experienced with doing a lot of trigonometry problems, then you will straight away recognize that you can split this, you can convert this into a sum of cosines and then straight away cancel it out. So really, the main message behind this problem would be that you need to always know the motive behind solutions, and constantly know, whenever you don't know how to do a problem and you're reading the solution or just watching a solution, then always know, like, how did this person, why did this person do it and do this method, and how did they know why they had to do it? And whenever you're doing problems too, like, always think about if the method you're about to use is intentional in bringing the result that you want. So yeah, that was kind of unnecessary to say, but it's what I feel about doing math problems. So yeah, thanks for watching, and see you in my other videos.